All right. So we have about 3.5 weeks of school, quite a few of which are 3 or 4 day weeks, before our SDC exam. So SDC exam is on either the 17th or the 18th. I would predict the 17th. It's like the very first state dual credit exam that they're doing. Very fun. And so what I want to start doing as we kind of start into Unit 6 here is I want to start some of our kind of review process while we are taking a look at some of the new content as well. So today what we're going to do, we're going to focus on kind of a holistic overview of what Unit 1 was about. And then I have a module for you guys to work on if you have finished all of your Unit 5 classworks. Otherwise, at the end of class today, you'll have some time to catch up on some of the classworks that maybe we've missed. So we'll go ahead here. Okay. So we started out chapter 1 in a bit of a weird. This was a combination of stuff that you guys should have seen before in other classes with talking about correlation. But also just from a statistical perspective, we're starting out with like comparing the relationship between multiple random variables when we haven't even established what a random variable is. So a little bit of an awkward kind of place to begin, but certainly kind of building on some ideas that we should have already known. So 1.1 was focusing on the correlation coefficient. Which we denote as R. And so we're going to be talking about the correlation coefficient, about this R value. Two, I would say, defining characteristics of every single R value as they pertain to correlation. So what are our defining characteristics for R? What do we need to know in order to be able to talk about the correlation between two variables? Strength is definitely one. So we'll unpackage what that means momentarily, but absolutely strength. And then what else? What do you mean by form? Positive or negative? I would maybe describe that. I don't hate form. I would describe that as direction, maybe. Direction. Yeah, but I don't dislike form either. The direction of the correlation, which I think you've done a good job of describing here. Often this is either going to be positive or negative, but we could also have no correlation, which kind of fits into both strength and direction. It kind of gets at a correlation where there is no strength, and because there is no strength, there is also no direction to it either. So that is great. So let's take a look at a couple of different correlations here. And let's see if we can't describe what we would expect to see with those, like what we mean when we say that a correlation is particularly strong. But actually, to that end, what does it mean for a correlation to be particularly strong? Like if I say that we see a really strong correlation between ice cream sales and murder rates, what is the implication there? Okay, so mathematically, we can talk about what that's going to mean with the R value, which we'll put a pin in that idea and come back to it. But that's spot on. But just like conceptually, before we start introducing like numbers into it, what does it mean for two variables to be like related? Yeah, exactly. One is affecting the other. So a change in one variable should produce like a fairly predictable change in the other. Okay. So let's consider our correlation. We'll create one here. We'll say something like this. Like what we see here. So let's talk about the relationship between these two variables that we're considering. We'll call this X, we'll call this Y. What do I know if I tell you that the X value that we are looking at is particularly large? So I give you like some kind of X value like over here or something. What kind of predictions would we make about the Y value? We'd expect to say that as our value of X gets bigger and bigger and bigger, we would expect to see larger and larger and larger values of Y. And for instance, if I gave you a particularly small value of X, what would we expect to see? We'd expect to see a Y value that is pretty small. How accurate do we feel like that prediction would be? For instance, do we have a lot of data points that maybe contradict this motif of a large X value giving us a large X value or a small X value giving us a small X value? Do we see many that are telling us otherwise? Anything that doesn't really feel like it fits the bill? Or do they all kind of tell that same idea for the most part? How good would you feel about your prediction that a large value of X should give us a large value of Y? Probably pretty good, right? There aren't a lot of data points that contradict that story. I would say, okay, maybe there's like, maybe this one right here, maybe. But even then, like it's not even that different from what we are seeing overall. And so when we have this kind of narrative and we have a lot of confidence in the predictions that we are going to be trying to make, this is what we are going to call a strong correlation. Okay. Which is to say that the changes that we see in X give us a good, solid indicator for the kind of changes that we would see in Y. Now, importantly here is that we are, in fact, still seeing changes, right? If I were to, and we'll look at an example like this here in a second, if I were to give you an X value that could be anything and a Y value that's just staying the same, we might have a high level of predictability, but that doesn't necessarily mean that the correlation is strong. So it's important both that changing the X is changing the Y, are not like causing the change, but that the changes are linked, but also that there's a high degree of predictability there, that we have a certain amount of confidence that, in fact, our predictions would be true. What else could we say about the correlation that I've described, that I've drawn here? So it's strong, but what else is it? Positive? Yeah. Which is just like a linguistic way to describe that like big X should happen around when big Y happens, and small x should mean that I have small y. In general, right? The larger my x value, the larger my y value. We could also have a strong negative correlation. I don't want strength and direction completely independent of one another. But in this example, we're seeing this strong positive correlation. Okay, let's take a look at another here. All right. Sure. What would we say about this correlation? If I gave you a large value of x, what kind of prediction would we make here? Well, maybe not necessarily negative, but maybe small. Okay. Yes.
But the brand name is all have
Here.
Okay. So those are the three things. Oh, yeah.
I'm sure your homework in on time.
Here's your
I don't know if you
mom.
remember across the street.
Yes.
Sorry, I forgot that.
No. Do you know what they're called? That's like your house. See if you're already house and coming up 5 years.
Yeah. Okay, so Paxton here said if I give you a large value of x, that we are likely to see a small value of y. I agree with that assessment. But how does our confidence compare to making this prediction versus the prediction that we were making over here? Do we feel more confident about saying that we'll get a small value of y here, or less confident? Less confident, because we see counterexamples. Right? We see instances in which a large value of x gives us a large value of y, or in which a small value of x gives us a small value of y. We see here that this idea, this link between our variables, is not always consistent. This is maybe not a weak correlation. This one's still probably fairly strong, but it is certainly a weaker correlation. But we'll label it as a weak correlation. So still a connection between our variables. But now the predictions aren't as good. Now we're not quite as sure that, in fact, what we are seeing here is giving us kind of reliable guesses. But on top of being weak, what else could we say about this prediction? It's also going to be negative. Very good. Of course. If I don't see you, have a good break.
Thank you.
And all negative means in this context is small. Well, we'll start with big again. We'll say big X, give us small y. Just how we're doing this. And small x, give us big Y. In general, all right, on average. Okay, so those are the main two. But they are not the only two. So the third option for third third option for type of correlation that we can see is we could also see no correlation. And no correlation is interesting in that there are a couple of different ways that we can get no correlation. There's not like one fixed kind of set way that is going to come about. All right, should be open, huh? Yeah. So we're going to look at two here, two different ways that we can get no correlation. The first one is probably the one that people are most used to, which is the idea of I have no correlation because if I were to try and make a prediction, it would just be a random guess. This would be an example where it doesn't really feel like changing my x is giving me a predictable change in my y. It's very chaotic. Yes, my y is changing, but it doesn't seem to be changing in relation to the x. There isn't like a definite pattern to it. We don't have any kind of fixed ability to make predictions. And so we would say that there doesn't appear to be any correlation. It's an unpredictable kind of change. So this is chaotic, not able to make good predictions. This is no correlation. This is not the only way that we can have no correlation, though. I think a subtle kind of other example here that we could certainly see is an example, we talked about this a couple minutes ago, but an example like the one that we see here. Where, for instance, if I asked you, or here we'll do even better than that, we'll do like this. If I gave you that we got a relatively large value of x, what would you predict about the value of y? Stay the same, fairly large, but like y is not changing. Would we be able to make predictions about what y should be given a value of x? Yeah, if we knew what this y value was, then absolutely we could make predictions. But do those y values seem to be coming about in relation to my change in x values? Is changing my x values linked with what might be causing the y values to change? Is there anything changing the y values even? No. And so here we have high but changing my x doesn't seem to matter. So we can either have no correlation where, yeah, my y is changing. We're seeing variance in my y, but there doesn't seem to be a pattern connecting the change in x and my change in y. Or we could have a situation like what we see here where, yeah, we can make good predictions, but those predictions aren't because we know the value of x, it's because the value of y is constant. It's because nothing is changing here. You can also see something similar with like a no correlation setup like this. This would also be no correlation, right? If I gave you that we have a particularly large value of x, or rather a value of y, that is not important information, right? That does not really determine anything. All right, questions here about our correlations, types of correlations. And what it means to be correlated is kind of the other key thing that I want us to understand. This feels very familiar, not too bad. Okay. Paxton, you mentioned earlier that there is a mathematical, a quantitative way to kind of capture it, and that had to do with the R value. So what did you say is the relation between the R value that we are getting and the strength of a correlation? Yeah, very good. So we can use the R value to describe the strength that we see here. And so the way Paxton has described this is, I think, perfect. I spin it ever so slightly differently, just to kind of detach the whole like directionality from it. But we can think of maybe like if the absolute value of R is closer to 1, then we have a stronger correlation. This kind of similar to the way you did by talking about +1 or -1, eliminates the need to refer to kind of either being positive or negative, right? We wipe out the directional component. We don't care about the direction of our correlation. Instead, we're just focusing on the size. We're just focusing on the magnitude of the particular value. What do I know about the R? What is it kind of like trapped between? It's trapped between -1 and +1. Another way to say that would be to say that like the absolute value of R is going to be less than or equal to +1. Almost like it's a probability. It's not a probability. R isn't a probability. R squared, though, is actually a probability. R squared gives the probability of, if we pick a random data point from our data set, of finding that data point on our regression equation. So for instance, if our R squared value is 0.9, then 90% of our data sits on the equation itself, is predicted by the equation. All right, very, very good. So if I were comparing, let's say, an R value of like -0.832 with, let's say, like an R value of 0.814, which of these represents a stronger correlation? It's this first one, that -0.832, because its absolute value is 0.832, which is closer to 1. Right? So that positive, that negative, that doesn't help us figure out is what we're looking at strong or is what we're looking at weak. That's saying something else about the correlation. What is that saying? What would this what would the positive or negative be telling us? Yeah, it's going to tell us the direction. So for instance, the -0.832 tells us that we have a fairly strong negative correlation. And the +0.814 tells us that we also have a fairly strong positive correlation, but it's slightly weaker than the correlation that we see for the other. All right, so the positive, negative, that has no bearing on strength. You have to take the absolute value, and then that's what you're comparing. All right. And of course, we can calculate the R value. I gave you an equation on like day 1, and it was awful and terrible, and we used it once and then never used it again. So that's not, generally speaking, how we are going to go about finding the R value. Instead, normally we do the linreg, right? Stat. Oh, actually, I think I just ruined my, yeah, I just ruined my L1, L2. Okay, we'll just enter in some like random values. Sure. Okay, normally we would do like stat linreg, but what do I have to make sure I do before I do this? There's some setting that I need to adjust. Give you a hint, it's under mode. Yeah, exactly. We just need to make sure that stat diagnostics are on, and then we're good to go. So in this case, my stat diagnostics are on. So we should be able to run this. So stat calc, then reg, enter, enter, enter. Okay, and in this case, I get a bit of information here. We get a couple of things. This is going to be slightly spilling over into 1.2. So we'll go ahead and start this. This is our linear regression. This was y is equal to ax plus b. We got an a value of negative 0.1221. So a b value of 4.9736. All right. And we got an R value of negative 0.1202. Okay, so what does this R value tell us? A weak correlation, if there is any correlation, and that it is, what else? Weak and negative. Yeah, very good. And we could confirm that if we go to our stat plot, which we want to be on, and go to this, do zoom stat, zoom stat, get the obligatory ad. Thank you. And we get this, which if I asked you like, okay, if I have a particularly large or particularly small value of X, doesn't really feel like makes a lot of sense to be making predictions here, right? This apparently has a slight negative correlation to it, but certainly not one that feels necessarily particularly significant. All right. Now the linear regression also gives us more information than just the R value. It also is giving us the full equation that goes alongside this R value. So in this case, our equation would be this y hat is equal to negative 0.1221 times x plus 4.9736 as a line. A couple of things to note here. First and foremost, this is the best possible R value, the strongest possible R value that we can get from a line. So this equation here is the line that corresponds to the strongest R value. For any line. Right? We can try other lines, they're not going to fit as well. And therefore, it is often called the line of best fit, because it's the line that fits the best. Now, that is not necessarily to say that it is the equation that fits the best. What you would have to do in order to check that is you would need to, for instance, maybe run other regressions and see, are there any other regressions that do better? For instance, here, we could run like a quadratic regression. And what we see is actually the quadratic regression does a pretty good job of starting to explain this data. It's a lot more likely that this would be quadratic than that it would be linear. You see this R squared value is like 40 times larger than the R squared value from the line, which is significant. That is a much better job. But as far as lines go, this is the best one we can get. So not necessarily the best equation, certainly the best line. As it stands, this is a population parameter. Thinking kind of like mu and sigma, rather than a sample statistic. Okay, so this is kind of incorporating a little bit of what we did in Unit 2 into the mix. So quick vocab review here. What does it mean to be looking at a population parameter versus a sample statistic? What's the difference between the two? Maybe towards the tail end. I don't think at the beginning. I mean, it's very similar to just the population sample. Mu and X bar both describe the mean, but X bar describes the mean of the sample. Mu describes the mean of the actual population. Why do we take samples? Like, what's the point of the sampling process? So we could talk about variance as a measure that we get from the sample. We could also talk about mean as a measure that we get from the sample. We can even talk about this equation as being something that we get from a sample in this case. But what do we use them for? Like, for instance, if I were to pick 5 people out of this room and look at whether or not they were wearing earrings, 5 people at random, am I happy to just leave that there? Am I just using it to describe those 5 people that I just randomly picked out of my population? Yeah, exactly. You'd probably be using it to try and either generalize or make predictions about what you would see if you looked at the population as a whole. So think of the sample statistic as giving us something that it's like an estimate that we're going to use to predict or generalize. Whereas, like, if I look at every single individual in a population and say this is the mean, that's not a guess, that's objective, indisputable fact. right? So the population parameter is this objective, descriptive value, right? We're not actually trying to use it to predict anything. We're just saying, hey, this is the mean. Or, hey, this is the standard deviation. There's nothing disputing that fact. If I tell you that mu is equal to 4, that means that the true mean of the population is equal to 4. Whereas if I tell you that x bar is equal to 3.5, that tells us that our guess for the mean is equal to 3.5. Okay. So for the data that I gave, I put in 10 data points to get this equation. If those 10 data points are my population, then this is a parameter. It's just describing what those data points are doing. Often, though, we don't want to use this as a parameter. We would rather use this as a statistic to make predictions. Okay. The way we do that, fairly straightforward, right? What would we do if I gave you that like x is equal to 13? Yeah, we would just take this 13 and sub it in for x, enter it into our calculator. That wouldn't be too bad. What if I told you that I wanted to know what's going on when y is equal to 2? Yeah, we just need to take this 2 and sub it into y, and it requires a little bit more work, right? We'd actually have to solve for y. How would we do that? If I set up my equation as 2 is equal to negative 0.1221x plus 4.9736, how would I solve for x here? Yeah. Okay. And then what would we do?
You divide both of the numbers by negative 0.
Yep. And doing that would give us, so dividing by that negative 0.1221 on both sides in order to get whatever that value of x actually is. Okay, not too bad. Now, that being said, we go about doing this, we make predictions about what y and x are. But like, how confident should we be in these predictions? How likely are these predictions to actually be describing reality? Should we feel good about these predictions? Are we happy with our regression equation? We think it does a really, really good job of predicting the future. What facet of it is going to tell us how good of a job it's going to do at predicting? What value could maybe carry that information? How do we describe the correlation here? We said it was... Yeah, the R value. So what does the R value tell us? In this case, that's telling us that weak, maybe negative correlation. So we'd expect to maybe get weak predictions from our weak correlation, right? If I'm looking at like a data set like what we see here, and I tell you what's going on at x equals 5, we should not feel that confident that that's reality, right? This is not a particularly strong correlation. There's probably a fair amount of error. Honestly, it's a little surprising that there's even a correlation at all, if there is even a correlation at all. So if this is a population parameter, then there is a correlation, right? It's weak, that's fine. But if this is just from a sample, this is not very good evidence that what we are looking at is in fact a correlation. Right. So 1.2 is like the machinery that we are using. 1.3 is when should we actually be using this machinery? When are we actually happy enough with our result to want to go ahead and run this kind of regression? When are we going to do this? Okay, so for 1.3, a couple of things that I want to observe here. The first thing, so this is for hypothesis testing, and this is going to come back in Unit 6, so I'm kind of priming us to do a little bit of that thinking of what we'll see in Unit 6. We're going to incorporate a little bit of what we did in Unit 5 here as well. So the main thing that I want to note for hypothesis testing is that if there is in fact no correlation, if the true value of R is equal to 0, so this would be literally if no correlation. Then if we were to take a sample, if we take a random sample from our data, we should be pretty surprised, or maybe we would be pretty surprised is a better way. We would be pretty surprised to see a sample with a strong correlation. And in fact, the stronger the correlation, the more surprised we should be. Okay, so what am I describing here? Well, let's consider a population that has no correlation. Right, we'll just throw up some random dots. Right, very clearly no correlation here. And I take a sample of this population. Most of my samples are probably going to look fairly similar to the population, right? We're going to get like stuff like this, or maybe like stuff like this. But some of those samples aren't going to look like that. For instance, if I do this enough, I am going to get a sample that looks like this. So our population has no correlation, fairly clearly. But what do the red dots show? If I only look at the red dots, what would I assume to be true about the population? There does seem to be a correlation. There seems to be a fairly strong positive correlation. And I could do the same with a negative correlation too, right? If I am just doing a bunch of random sampling, I can find dots that make it look like I am looking at a negative correlation. But that shouldn't happen very frequently. If there is truly no correlation here, this should happen not often. And what not often means, we'll define here in a second. Okay, but I want it to be clear, like, yes, this can occur, but it's probably not going to happen by just random chance. It certainly can, but it's probably not. A lot more likely would be us getting the kind of red dot esque R value from something more like this, right? There are a lot more ways to circle 4 dots and get a similar R value, right? And so going from a population with no correlation to a sample that has a strong correlation is a lot harder than going from a population with a correlation to a sample with a correlation. It's significantly harder to do it. It's a lot more rare. And so if we were to see something like this, this should make us skeptical. We see this and we say, now hold on a second. Is this actually coming from a population that has no correlation, or is there in fact something more like what's going on the right here? And we might be inclined to more believe the story on the right. Should be more likely, should happen more frequently. All right. The other thing that I kind of want to note here, and this is not something that's like directly relevant, but it is still something that I think is kind of important, is the idea that a larger sample should make these extreme cases even harder to happen, right? If I pick just 4 random points and get a strong correlation versus picking 8 random points and getting a strong correlation, well, it should be a lot harder to find 8 random points that are giving me the strong correlation. So a larger sample size makes this even more unlikely. Okay. So what is actually going on here? Let's take what we did in Unit 1. We're going to mesh it with what we've now done in Unit 1. Right, so this was our Galton board. This was our demonstration of the central limit theorem. My claim was that even if we don't know the distribution of our population, that if we did enough sampling, or if our samples were large enough, that it shouldn't matter. If n is big enough and we don't know what's going on with the larger population, it's still going to work out to be a normal distribution. That is also going to be the case with our R values to some extent, right? If we were to sample enough, if we were to collect enough data, we should expect our R values as well to kind of start forming something that looks similar to a normal distribution. Okay, so let's say we pick one random marble from what is kind of resting at the top here, and I wanted to make a prediction for where that marble was going to end up. Where would we maybe guess as far as, what would maybe our like best possible guess be for where any random marble is going to end up if we track that one marble?
One of the columns this time.
Yeah, one of the middle columns, right? We saw that with our normal distribution, that one marble is most likely to fill in probably one of these like middle four. Now, does that mean it's impossible for a marble to land here? No. Even if the mean is the same, even if the expected value is the same, it's possible to get a sample that does in fact hit kind of this outlier case. And so that is kind of something that we understand, like, hey, it's possible that we get this bizarro circumstance of like, we picked just the worst 4 possible data points, and they happened to tell us that there was a strong correlation. We recognize that. But assuming that that didn't happen, or rather, we can't really assume that that didn't happen, but we want to put ourselves in a scenario where that happening should be difficult enough that we can be fairly confident that that's not what's going on here. This was kind of what we were doing with, we were setting like the alpha value equal to 0.05. We're saying we want to be 95% sure that what we are seeing here is in fact because of there being a correlation rather than just gradations. Anything that's in these kind of inner buckets is probably a little bit too likely. As soon as we start to see something on the outside here, maybe we should get a little bit skeptical about whether or not these marbles are in fact following the same kind of pattern of these others. Now, in this case, they are. We're sampling enough of them that we actually will have marbles that fall into the extreme cases. But it's not very likely. And so we can say with a fairly high confidence, if we're just looking at one random sample, that it's probably going to be a random sample coming from here rather than a random sample coming from here. Okay, so how does that relate to our R values? Well, we're essentially going to be treating this like a normal distribution. I'm not claiming that it's actually a normal distribution, but the thought process is very, very similar. So we have our normal distribution. What would if we're assuming no correlation, which we are going to assume, what would our expected R value be if there is truly no correlation between these variables? Yeah, this should be like R is equal to 0 is our expected. And yeah, maybe we see something like over here of like R being equal to 0.14 or something over here of like R being equal to negative 0.12, things like that. But that's just kind of like the fact that samples don't always follow the sample mean. We expect them to be relatively close, but we would not expect it to necessarily be exactly equal, right? Okay. So what this 0.05 is communicating is it's saying I only want from this kind of graphic here 5% of my graph to account for these kind of oddity variance kind of pieces here. And so if we go out far enough to where we have 95% of the data kind of trapped between these values, trapped between these R values, (95% of our data here). Then how much of our data is going to be excluded from this particular kind of bucket on either side? So for instance, how much of my data is fitting here? How much of my data is fitting here if this is 95%? 2.5% on each. And so we could think of this as like the bottom 2.5% on our left, and then the top 2.5% on the right. And we're saying if we see an R value that falls within the bottom 2.5% or the top 2.5%, that's unusual enough for our just no correlation, for our no correlation setup, that we should probably be suspicious that there is in fact no correlation. It's more likely that in fact, if we get something from over here, so if we're getting values from over here, or that are over here, that really these are coming from the from something that looks more like this. Again, it's not impossible, just more likely. We're 95% sure that we'd be getting values that live in the middle here rather than on the outside. All right. So this is, think of it as like being part of our threshold for what we consider like what's good enough. We're going to be wrong about this about 5% of the time as well, right? If we were to run 100 simulations, if we were to take 100 samples, we'd expect 5 of those to give us our values that live here. But that's just what it means to have like this 95% of our data covering in between. But we're saying that's good enough. If we're taking one random sample, then the likelihood of being one of those 5 is low enough that we're okay with taking that risk. Unless we're not, in which case we have to adjust the alpha value. Okay, so alongside this, we have the idea of our hypotheses for this test. There is what is called the null hypothesis, and there is what is called the alternative hypothesis. What does the word null mean? Nothing. And so if my options are either my hypothesis of having a correlation or not having a correlation, which should my null hypothesis be? Not having a correlation. So H sub 0 is going to be that there is no correlation, or we haven't seen it this way yet, but this is ultimately what this means as well, the idea that the true parameter is equal to 0. Right, which is saying that it matches our proposed mean up here. Okay. Alternatively, if that's false, what must be true? That there is a correlation. And if there is a correlation, then what do I know about my population R value? Not necessarily that it's like super strong, but we know that it's not 0, right? Certainly we know this. We don't necessarily know how strong it is, but we do know that it's not 0 if there is, in fact, some kind of correlation here. Okay, so this is just, again, another way to say that there is a correlation, which is that the population parameter is 0 or not 0, depending on whether it is true or false. All right. Awesome. So we take a sample. We'll give it a sample size of 12. And we'll say that the R value that we get is negative 0.593. So moderately strong. Is this strong enough to suggest that we have a correlation? Does this fall within that 5% chance? Does that fall within the top 2.5%, or in this case, it'd be the bottom 2.5%, or is it not good enough? Okay, this is where we needed to bring in the table here. Okay, so this was our kind of way to determine, is our R value actually strong enough, or are we not convinced by what's going on here? You'll notice here a couple of things to note. First and foremost, that having more data, having a larger sample size, lowers the threshold. It raises the difficulty, so we don't need to see as big of an R value to be surprised.
If we increase the samples.
Yeah, we're increasing the sample size. It's harder and harder to get really, really big R values. And so it raises the difficulty, which lowers the threshold of what the R value needs to be when we are surprised. So for instance, like 0.5 might not be super surprising if we only take like 3 data points. But by the time we get to taking like 50 data points, all of a sudden 0.5 is pretty hard to get just by a random chance. Okay, so what on this table is going to be our degrees of freedom? If our sample size was 12, how do I convert taking a sample of 12 and getting the, like, where on the table it's going to be? What do we have to do? Yeah, we look at the leftmost column, and where is my n being equal to 12 going to be located? It's at 10, right? Remember, for this table, we have this whole, we have to subtract 2 from our sample size to find the degrees of freedom. And it'll be different for tables. I think chi-squared, you subtract like 1 or something, but it depends. And so we are going to use 10 here as our degrees of freedom. What was our alpha value? Did we say that we wanted to, it's like the general one that we're pretty much always going to use. 0.05. And so what is the threshold for when we should be surprised? That right there, that 0.576 is the point at which we should pause and say, now hold on a second, this is suspiciously strong. If we got an R value that was exactly 0.576, I'd probably say we default to, I actually don't know. I don't remember if you fail or succeed on exactly that point, but the likelihood of getting exactly that value is so small that it's like not even worth talking about. You're probably going to get something that's either weaker than this or stronger than this. In our case, if the table value, which is also known as the critical value, so the critical or table value, was R is equal to 0.576, how does our value compare to what we see in the table? Is it stronger or weaker? And does that mean it's more rare or less rare? Stronger, therefore more rare, exactly. It's less likely to see an R value this strong than an R value this strong because it's stronger. And so because it's stronger, we have good evidence that we should be suspicious, that something is maybe afoot here. And the thing that is afoot is the idea that this is wrong. So we generally assume that the null hypothesis is true. And what we're saying here is that what we have found is an R value that beats that R value threshold that we are essentially setting. If we were to kind of put R values to this normal curve, the fact that for this table, we're seeing an R value of 0.576, think of that as being almost like a Z-score. This would tell us that 95% of the data lives between negative 0.576 and positive 0.576. And so where does negative 0.593 live? Well, it lives in the kind of magenta region. And the magenta region is the region where we should start to be suspicious of whether or not the null hypothesis is even true. And by suspicious, I mean we should probably start to suspect that it's not true. Because the likelihood of landing here or landing here, that only happens 5% of the time by random chance. And so it's so strong that we don't have a lot of confidence that this is in fact the kind of framework of reality. And so because, and you don't have to write all of this, but we'll include, so because our R, or we'll say our R, is stronger than what we see on the table. Stronger than the critical value of 0.576, we reject the null hypothesis. And rejecting the idea that nothing is happening is the same as saying that there is evidence, there is strong evidence of a correlation. Yeah, we actually do have good evidence because seeing an R value as strong as negative 0.593 from a sample of 12 should only be happening It should be happening less than 5% of the time, seeing something that strong. And so we say, well, if that's going to happen less than 5% of the time, then it's more likely that this is not the actual population, that this is not the correct normal curve, that in fact the R value is somewhere else. Probably more negative, right? Probably this way. Now, if we did not have a strong enough R value, if our R value instead was like 0.54, it's weaker than our table, have we successfully proven that there is no correlation? No, we have not. All we have done is failed to prove, or not even, we're not even proving that there isn't, but we have failed to produce strong enough evidence to make the claim that there is no correlation. All right, so if our R value is too weak, then we don't affirm the null hypothesis. We say we fail to reject the null hypothesis. And if we fail to reject the null hypothesis, then we will continue with the assumption that there is no correlation, and we'll just move on. Right? Moving on can be maybe collecting a bigger sample and then coming back, but it would not be enough for us to like say anything definitively, essentially. All right, questions with our hypothesis testing here, 1.3. Feels okay. We're gonna feel really good in Unit 6 when when we're having to do all this again. I'm making a couple of adjustments here. Cool. Awesome.
Can I take a picture of that?
Yeah, go for it. Okay, so that's most of what we did in, that's most of what we saw in Unit 1. The only other thing was correlation versus causation. So, you know, high ice cream sales being correlated to high murder rates does not mean that selling ice cream makes people more stabby. Correlation is not the same thing as causation. What's the buzzword that we need to see to say causation? We need to see the word experiment. Before I said it was either experiment or study, but there are observational studies that are not good enough for us to claim that what is going on is causation. So if you don't see the word experiment, I don't know if this is how the SDC is doing it, but this is the right way to do it. So this is how we're gonna cover it. If you don't see the word experiment, or if what is described is not an experiment, then we do not have sufficient evidence to claim causation. It has to be specifically an experimental procedure.
So I can make the difference between studying and
Yeah. Yeah, important to be able to figure that out so that we can say, can we say causation or correlation? Yeah. All right, Unit 1 in an hour and some change. Like a week and a half's worth of content, all packaged nicely. Okay, we have about 15 minutes left, a little bit less. So you guys have the rest of this time to either work on any Pearsons that we are missing, or to get started on the Unit 1 review module, which is in the SDC review folder on Schoology.
Teachers, pardon this interruption. Students, teachers, everyone, I just want to say to you all, congratulations on a great third quarter. I know we've already moved this first week into the fourth quarter. I know you guys are about ready for spring break to begin. Well, you won't have to wait any longer because teachers, we got a storm moving in. We want to get the kids out as quickly as possible. So if you will, go ahead and dismiss the students.
All righty.
Spring break, everyone.
Well, have a fantastic spring break, you guys. That was well timed.
I still have that class on the Saturday. Can I do it back again?
The which one? For on 5.7? You have until the Thursday we get back from spring break to get it done. So yes. Yes.
Maybe I need to get my grade up. 'Cause I'm really trying to figure that out. I need to retake the test we took, which I'll probably figure out
Yes.
after this.
Yes, we can do that, and then to be frank, here, let me stop the recording here.
Swipe down.
Cool, nice. To be frank, what we're going to be looking at from, although actually I don't know I think that stopped the screen recording.
Oh, my bad.
Yeah, you're good. No, that was smart. I didn't know you could do that, but we're gonna